In this video, we're going to take a look at section 3.2 on measures of variation. All right, so consider the following two data sets. This is how I always introduce this topic because it shows you the relevance of it, why it's really necessary. So here we have two data sets. We have data set number 1, data set number 2. In the first data set, we have the numbers 1, 5, 3, 2, 4, 3, 4, 2, 3, 3. In data set number 2, we have the numbers 3, 3, 3, 3, 3, 3, 3 repeated. And it's the same number of data values because I didn't want that to be the issue that we focus on here. All right. What are the measures of center? So I have a typo there already. Sorry about that. So I'm kind of making these as I record the videos. So sometimes I might not catch those typos right away. What are the measures of center? I want to look at all of them. And I think if I've done this correctly, they should all match up with each other, right? So what we want to look at, remember the measures of center are the mean, which we represent with X bar when it's a sample, which we should assume this is what we have here. The median, the mode, and the mid-range. And so let's calculate that for both of these data sets. Now, to calculate the mean of data set number 1, remember what we have to do. We have to add up all of these values. I believe there's 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like 10. I don't want to bother grabbing a calculator. Let's see if we can just do this without a calculator. All right, so 1 plus 5 is 6. Plus 3 is going to be 9. That'll be 11. 15. That'll be 18. 22. 24. And then 6 more would be 30, which is what I was expecting it to be. So we have 30 as our total when we sum up all the data values out of 10 data values. So to find the mean, we add up all the data values, divide by the total number of data values, and we get 3 as the mean for data set number 1. The median, we would need to organize this numerically from lowest to highest. So let's go ahead and do that right here. We have 1 just once. We have 2 twice. We have, so I better write it twice. We have 3, 1, 2, 3, 4 times. We have 4 twice, and then we have 5. It's an even number of data values, right? So, in both of these cases, n is equal to 10, right? That's the number of data values that we have. So that means there isn't a number exactly in the middle. So we have to actually take the 5th data value, right? So we take n, we divide it by 2, so we get 5. I don't know why the equal sign looked like that. We get 5, which means we want the 5th data value and the 6th data value. And I think the same thing's going to happen here that happened in the previous video, which is it's going to be the same number twice, which doesn't normally happen. So again, that's not very typical, even though it seems like every example I'm doing has that occurring. So the 5th value would be, that's 1, 2, 3, 4, 5. Here's the 5th one. Here's the 6th one. So they're both 3s. And so we add those together and divide by 2. And we again get 3. So the median is 3 for data set number 1. The mode, not the mole, like I think the same thing happened in the last video. The mode is the data value that occurs with the highest frequency, if there is one. And in this case, there definitely is. I made sure of that. So 3 occurs 4 times. That's more than any other data value. So the mode is going to be 3. And then the mid-range is you take the minimum plus the maximum and divide by 2. Our minimum value here is 1. The maximum value is 5. So that's going to be 6 divided by 2, which again is 3. And so for data set number 1, every single measure of center is 3. So by almost any way you could look at it, the center of data set number 1 is 3. What about for data set number 2? It's a little bit silly, but we're going to get the same answers, right? What is the mean of data set number 2? So again, follow the same course. Add all the data values together. We have 3 plus 3 plus 3 plus 3, 10 times. So we're going to get 30. divided by 10, the mean is also 3. The median, what number is exactly in the middle? It's the same issue as up here. You want the fifth data value, 1, 2, 3, 4, 5, and the sixth one. They're both 3s. You average those two numbers together, you still get 3. So the median is still 3, right? So just like we did up here, I'm sorry it got kind of messy, but add the two numbers together, divide by 2. We're taking an average of those two numbers. The mode, now this one you maybe could argue, I talked about this in the last video. There's only one data value here. So there isn't one that occurs more frequently than any of the other ones. So you maybe could argue that this data set doesn't really have a mode because it doesn't have a data value that occurs more frequently than the other data values, right? It's really a comparison thing. But again, 3 occurs 10 times. So if they're, I don't know how I want to, I guess I'm contradicting myself here, but I would say if we're going to have a mode, in this case, it would be 3, right? It occurs 10 times. Way more than any other data value, which there are no other data values. So I guess that argument could be made as well, is that it still occurs more than any other data value, right? Because it's occurring 10 times. It's the only one. It's more than any other one. So either way, I didn't really think that through when I set up this example. I just kind of assumed the mode was going to be 3 here as well. And then the mid-range is going to be 3 because we're going to take the minimum, which is 3, plus the maximum, which is also 3. 3 plus 3 is 6. Divide that by 2, you get 3 again. The point being that by comparing the measures of center, these data sets look identical through that lens, right? So through the lens of the measures of center, data set number 1 and data set number 2 are indistinguishable from each other. They have the same exact measures of center. Yet when we look at them, the actual data values, there's clearly a fundamental difference between data set number 1 and data set number 2. But you wouldn't know that by looking at the measures of center, right? So is there some aspect of the data sets not addressed by looking at the measures of center? That's the next question. And the answer is yes. What's not addressed by the measures of center is the variability in the values of the two data sets. Measures of center are blind to that variability. And so measures of center alone don't give you enough information about your data set. So if you're trying to analyze what's going on with these numbers, just looking at measures of center is not going to be enough to have a good sense of what's going on, right? So a good way to see that is to ask yourself this question. It's the last question on this screen. Would a data value of 2 be unusual to see in the first data set? The answer is no, because we actually see it occurring twice, right? And so if you were to imagine, I don't know where this data is coming from, I just made it up, but let's suppose these numbers actually come from some kind of measurement. And I got these 10 values. Let's say I wanted some more data to work with and I was going to go back and collect more measurements. Would you be surprised to see 2 occur again if I went back and got measurements from wherever data set number 1 came from? No, you wouldn't be surprised. You see it twice already. It's a fifth of the data values that we already have. So it would not be shocking to see a 2 occur if we were to collect more data in data set number 1. Would it be unusual to see a 2 show up in data set number 2? Yes. We would be surprised by that because clearly data set number 2 has established a pattern that the answer is always 3. Wherever that measurement's coming from, it's always 3. It would be surprising. It would be unusual for a 2 to show up there. And you wouldn't know that by just looking at the measures of center because through the measures of center, the data sets appear the same. But there's a big difference because 2s are common in data set number 1, whereas a 2 does not even occur in data set 2. So we would be surprised to see it occur if we were to collect more data. Right. So I hope that helps you understand why it's important that we don't just look at measures of center when we're looking at a set of data, but we also need to take into account the variability in the data. And it helps us understand that data better. So we can understand that in data set number 1, 2 is not unusual. We should expect that kind of a number. In data set number 2, it is unusual, even though the measures of center are the same for both data sets. All right, so how do we measure that variability? Turns out it's kind of a difficult concept to capture as a measurement, right? Because we want to kind of boil it down to a number, just like measures of center. We boil it down to a single numerical calculation, right? The mean is a number. The mode is a number. The median is a number. So we want to find some way of quantifying the measure of center as a single number, which we did in the previous video. We want to do the same thing for measures of variation. I want to be able to boil that concept down to just a single number in my calculations. A measure of variation is a calculated number that represents the spread of values in a data set. So how can we calculate the way the numbers are spread out? Well, a very simple thing you can do is to find the range of your data set, which is the difference between the minimum and maximum value. Not to be confused with the mid-range, which is the number halfway in between the minimum and the maximum, right? So the mid-range, we add the min and max together and then divide by 2. For the range, we take a difference, which means we are going to subtract the maximum minus the minimum, and that gives us a really rough idea of the spread of data values in our data set, right? By saying what's the gap between the highest number and the lowest number. It's not a very useful gauge. We need something a little more sensitive, a little more fine-tuned than just what's the biggest number and what's the smallest number. But it's a good start. All right, so let's find the range for the Animal Crossing critic review scores that we've been looking at since the beginning of chapter 2. So the range here is going to be the maximum minus the minimum. The maximum value in this data set is 100. The minimum data value in this data set is 70. We subtract those two and we get a range of 30. So the range for this particular data set is 30. It's a very simple, easy calculation, and it gives you a really basic sense of how spread out the data is. And so does it really capture that variability very well, though? That's, not really. The range doesn't do a great job of capturing the variability. The range is very susceptible to outliers. So if you had one number that happened to be far away from the rest, like if we just had one critic, like Anton Ego, right, in Ratatouille, right? He's just a negative ninny. I don't know how you say that. He's a negative personality. And he just hates everything, right? So if there was an Anton Ego of, video game reviewers, that person might give Animal Crossing a rating of 50. Everybody else is up here in the hundreds and 90s, but that one person doesn't like any video games and they rate it a 50 no matter, even if it is a good game, right? Now the range is going to be 50 because of that one person. Maybe that's what's going on with the 70, because if you exclude the 70, the next lowest score is an 80, and the range becomes 20 instead of 30. So all it takes is one negative person to give it a bad rating to stretch that range out, when really the variability isn't quite that extreme, right? That was just one person really far away from the rest. Most of these reviews are between 80 and 100, which isn't a very big spread. But because there was 170, the range makes that spread look more than it maybe really is. And so, like I said, that's kind of why the range isn't really capturing the nuance of this data set and the actual variability within these numbers. Right. So we need something more sophisticated. Right. Is there a better way of measuring the variation in a data set? And the answer is yes. It's more complicated. It's still not perfect, but it's better than just looking at the range. And I'm not sure where I'm going from here, because now that I think about it, I didn't get set up for this, but I wanted to do some calculations on a spreadsheet. So I think I'm going to need to pause my recording, get that spreadsheet set up so that we can kind of explore a better way of measuring the variation in our data set. So give me just a second. Okay, welcome back. So I went ahead and went to Google Sheets, found the spreadsheet that we were using in the previous video for finding the mean. And we will use this spreadsheet to explore another way of measuring the variation in our data set. So if you were tasked I don't know why I'm saying four, if you were tasked to find a way of measuring how the data varies, it might take you a while, but if you really gave it some thought, you might eventually stumble upon the idea of taking each data value in our data set and measuring how far away it is from the mean, because that would give you a pretty good sense of the, sorry, my phone's ringing, which is really unusual because nobody ever calls me or texts me. And so, but I'll have to get back to them later. Okay, there, it stopped. Okay, sorry. Because, so again, the mean, so one way of measuring variation is to say, let's define a center for this data set and then measure how far each data value varies from the center. That would be a good way of quantifying the variation in a set of data. What's the center, right? So the center is right here. So I'm using my hands, but you can't see it. So what's the center? And then let's find how much the data values vary off of the center. And so a good measure for center that we talked about in 3.1 is the mean. So we will use that as our definition for the center of our set of data. Again, it has some limitations, but we will, it's good enough for this purpose. And let's find out the variation. How much does each data value deviate? Let's put it in those terms. How much does each data value deviate from that center? So what we want to do is for each data value in the data set, let's measure its distance from the center, from the mean. And so if you remember, our mean, it's way down here, was 90.6. Right? That was our mean that we calculated in the previous video for this particular data set. So let's take the data values we're given one at a time. Again, you have to hit equals to make it do a math calculation. Take the data value in that particular cell, which is 100, minus that mean, which we decided was 90.6. We'll just probably, as we're doing this calculation, you don't want to round it off. When you're presenting it as your final answer, you want to round it to one decimal place. We talked about why in the last video. But when you're doing further calculations, you don't want to round it off. You want to keep it as exact as possible. But so it's a do as I say, not as I do moment. I'm rounding it to 90.6, but if you're going to do a calculation like this, you really should keep all the decimal places. All right. Just to be safe, just to make sure you get the exact answer you're supposed to get. So we get 9.4. So that's how far that data value deviates from the center. It's 9.4 above the center. And that's going to be the case for the next several because they're all 100. Now, I could manually type each one in, but that's going to get a little out of hand. And in terms of like how tedious and long that would take. So the best way to do this is to use, this is what the strength of an Excel spread, not Excel, the strength of a spreadsheet is that you can sort of formulate this in a structured way so you don't have to manually do each one, but you just, you structure it the right way, and then you just copy that structure down and it automatically fills it in for you. So I want to take this cell. So notice when I click on it, it doesn't put 100 in the cell, it puts F3. Which is the location of that cell, right? It's in column F, row 3, minus this one. I could refer to the cell where this calculation was at, but I'm just going to go ahead and manually type it in, which is 90.6. Now this time I'm going to hit enter. I get the same answer, right? It's 100 minus 90.6, which is 9.4. But if I look at it, I'm sorry, it's a little bit hard for you guys to see. It's just off the screen, my recording area. See if I can move this over here. But you can, I guess you can barely see it, equals F3 minus 90.6, right? So it's using cell F3, whatever value is located there, minus 90.6. So if I change that value, it'll change that calculation, right? So if I change this to 99, for example, now it's 8.4, right? So I don't have to, so if the numbers change, I don't have to go and manually change each one. It'll happen automatically. Like when the cell changes, the calculation automatically changes. What else is nice about this is I can copy that formula And the spreadsheet is smart enough to know when I copy it here that I want it to apply that formula to this new row, not to the cell from the old row that I'm copying it from, but it knows that I want to copy that formula and apply it to the row that I'm pasting it into. So when I paste it here, now you can't tell from the answer because it's the same number, but if you look up here, notice it's not F3 anymore, it's now F4. I pasted it into row 4, so it adjusts the formula to reflect that now I want F4. And so I don't know, I don't usually use Google Sheets. My experience is more with Microsoft Excel, but what you used to be able to do is you could highlight all of the cells and just paste it in there, and it'll paste it into every cell. At least you can do that with Microsoft. And it'll do the same thing. It'll adjust the formula for you. So that way I don't have to type it in one at a time. I don't have to even paste it one at a time. I can just paste it all the way down this column, Control V, and it automatically applies the formula to that cell in that particular row. So it's applying it to column F all the way down, but it changes the row based on where the formula is getting pasted. So it's just one, I have to type the formula in once, copy it once, paste it once, and I can get 107 different calculations immediately. That's what's great about spreadsheets. Now these are all 9.4, and again, you can double check just to make sure that's F9, that's F10. All right. Here, 95 minus 90.6 gives me 4.4. What I want to point out to you is that if it's below the mean, like this one is 90, the mean is 90.6. So this one actually deviates below the mean. That difference is going to be negative. It's going to be negative 0.6, right? So here, 86 is below the mean. So the difference is negative 4.6. So we get negative deviations as well. So if the deviation is positive, if the difference is positive, maybe I shouldn't use deviation, but if the difference is positive, then the result when you subtract will be positive. I'm saying that kind of wrong. I'm saying it backwards. If the data value is above the mean, the difference will be positive when you subtract. If the data value is below the mean, the difference is negative. So the sign tells you whether the data value occurred above or below the mean, which could be kind of useful, right? So I had 107 data values in my data set. I subtracted the data value, each of those data values from the mean, and now I have 107 deviations. I have 107 differences to look at, which doesn't really help you, right? We're trying to boil this down to a single numerical calculation. So one thing you might consider doing to boil it down to a single number is to add all those differences together. And let's not include the 50. Remember, I put 50 in there because of the median to have that even number of data values. So that's not actually part of the data set. So it wasn't part of our mean calculation. So let's leave that out. Now here's where I'm going to actually have to eat my own words, because like I use 90.6, which is rounded off. It's not the exact mean. So this is not going to be exactly what it's supposed to be. But what we could try to do to take all these differences, because a good way to think of it is I'm trying to find a single numerical measurement for the variation. So let's find how far each data value deviates from the center, and then add up all those deviations. Let's sum up all those differences, and that may give us an idea of how varied it is. But here's what happens when you add up all these numbers. It's not going to be perfect, but it's going to be close. So again, to get a spreadsheet to add these numbers up for me, you do equal sign to do a calculation, and then you type the word sum. I think I talked about this in the last video. And then you have to tell it which cells to sum over. It actually had a good suggestion there. Maybe I should go back to it. G2 to G108. And that's what we want to do. G1 was empty. We didn't have any data values in that row. We started at G2, and it comes all the way down to G108, and we're doing this calculation just below that. So I think that's what we want to do. Right, and you can see it highlights it for you to let you know, here's the numbers you're adding up. We hit enter, we get 3.8. So I was hoping it wasn't going to be quite as bad as that. So let me go back and change what I've done. All right, so that you can see, I didn't think this far ahead, and now I'm regretting. The reason, I don't want to give away what's going to happen. if I change my mean from 90.6 to be more precise, 6355, let's get that far, 4 decimal places. What do you think this sum is going to get closer to? I know what it's supposed to exactly equal, but what do you think is going to happen there? So let's change the formula, go back to the beginning, and instead of 90.6, and I don't want to copy the cell reference. I don't want to put like, A, whatever it was at, because then when I copy it to the next cell, it might bump it down too. It might adjust the row number which for the mean, we don't want it to adjust. We want to keep using that same number. So I'm just going to manually type it in, 355. All right. I'm just going to make that look more complicated. Now I will copy, Control C, highlight the rest of the cells, and paste it. So you might say, oh, we have to go back and change all of these. Very easy to do. Paste. All right. Okay, no, that wasn't very easy to do. What happened there? I forgot. The first cell, we didn't use the cell reference. We actually typed the number in. Okay, one more time. Oh, I'm embarrassing myself. Okay, let's try that again. It's F2 minus 90.6355. Yeah, the result we got of 1,000, like that just floored me. I was like, what just happened there? Okay, now let's copy and paste. That was the exact opposite of what was supposed to happen. So, okay, scroll down. All right, paste. Here's what was supposed to happen. So notice it's now. It was 3.8. And that, again, because I made the bad choice of using the rounded off mean. So I said, do as I say, not as I do. But then I just ended up making an example of myself by not doing what I said to do. When you're presenting it as a final answer, round it. 90.6 is great. That's where you want it to be. But if you have to take that number and do further calculations, you do not want to round it, because then your further calculations are not going to be what they're supposed to be. So what this should have equaled, and if you couldn't tell by how small this number got, is if I had used the exact value of the mean, if I didn't stop at the 5, but I don't know, let's just use all of it. Let's just see what happens in that case. Let's change it. Oh, I already forgot what the number was. So we have 3551402. All right. So we have 1402 at the end of that. Let's copy and then paste and see what happens. I was just trying to avoid all these decimal places, but really, especially with such a large data set, using that rounded off number was just a bad choice on my part. All right. And so now you can see it's not exactly 100% zero, because this value isn't exactly correct to the 8th decimal place. But it's practically 0.000000, which would round to 0. So the point is, I'm maybe taking a little too long to make my point, is that if you take every data value in your data set and you subtract that data value minus the mean, and add up those differences, it will always equal 0. It always zeroes out. That's just the nature of how the mean relates to the data set. And so you're basically kind of going backwards, and you're going, maybe backwards isn't the right way to think of it, but it kind of cancels itself out in a way. And the reason that's happening is because we are having both positive differences and negative differences. And the positive ones, for every data value that you have above the mean, there has to be sort of a mirror image value below the mean, because by the definition of the mean and where it sits, for every number that's above it, there must be some number below it, kind of the same distance away. And when you subtract, you get one being positive, one being negative, and they cancel each other out, right? And so that's why it negates. This sum negates itself, because for every value above the mean, there has to be an equally weighted number of data values below the mean, a certain distance away, so that it perfectly balances out and gives you 0 when you add these up. So the issue is having these negative differences. There's 2 ways we could possibly fix it. One way is to use an absolute value, right? So if you remember from college, so we're going to be talking about some algebra. College algebra is a prerequisite for this course, and sometimes students will question why it would be, a prerequisite because it's really a completely different mathematical subject, but there are different concepts, there's different things that we encounter in statistics that do call back to college algebra. And one of them would be, well, if we want to make all these numbers positive, what's a way we could do that? Absolute value would be one way. And in fact, in the textbook I can remember reading, that actually gives you a certain measure of variation, but it's one that we don't use. And the reason we don't use absolute value is because nobody likes absolute value. That's the joke I always like to make. Absolute value is difficult. If you can remember solving absolute value equations, absolute value inequalities in college algebra, you can remember they were kind of complicated. It turns out that they continue to be complicated even as you do more sophisticated types of math. So in calculus, absolute value is you can't apply the methods of calculus to an absolute value. And why that's important, and you're going to learn this later on in this course, calculus is actually really relevant to statistics. And you might be saying, oh gosh, am I in the wrong class? I don't know anything about calculus. This class is designed so that you can approach these statistics topics without having to know calculus. So we're going to enable you to still perform these statistical analyses and just let technology do the calculus part for you. It used to be before technology, we had these big charts that you can still use. Maybe when you got your textbook, you might have noticed it came with one of these charts, and you'll see these tables and tables of values. All of that is so that you don't have to do calculus. That's what all those tables are for, that purpose, so that you can avoid using calculus. TI calculators, which is normally the way we teach the class, will do the calculations for you so that you don't have to know calculus. The calculator does it for you. Right? But calculus is actually an important part of doing statistics. And calculus doesn't really work very well with absolute value. I don't want to go into the details of that, but it's an issue. It's a problem. So what's another way that we could make these numbers positive without using absolute value? Another way we could make them positive is by raising them to the second power. So that changes the number, which is kind of a bad thing, but it makes the numbers positive. And if they're all positive, they can't possibly zero themselves out. So what we're going to have to do is to take each of these results and raise them to the second power to make all those negative signs go away. All right. And so we're going to take the data value. So I'm just going to kind of write a header here. Data value minus the mean, and then raise that to the second power. That's how you would write that. So I'm not really sure how to do that on here, actually. I don't know if I can just do an exponent of 2. I might have to do something like pow, a number raised to a power. So pow. I don't know how to do it. Okay, I don't use parentheses, obviously. So pow, parentheses. Okay, so now it kind of gives me a structure of how I need to set this up. So the base is the number that we want to raise to the second power, which is going to be whatever number is in this cell right here, G2, comma, the exponent I want to raise it to. What exponent do I want? I want to raise it to the second power. All right, so we're taking the value from G2 and we're going to raise it to the second power. That's what that function is going to do. All right, and we get 87, which is about what you would expect, right? 9 squared is 81. This is a little bit bigger than that, so we get a little bit above 81. All right, so now we're going to copy and we're going to paste it all the way down to here. And now we get all of these differences squared. So we took the difference between each data value and the mean and then raised each difference to the second power. And notice none of these numbers are negative. So now when I add these together, I should get a number, right? And so we're going to sum. So I'm just going to actually, they suggest it here. So we're going to take that sum all the way from row 2 to row 108. And we get this huge number, 3,962.78. So we've boiled it down to a single number, and it didn't zero out. But the problem with that as our measure of variation is that it's dependent on the size of the data set. It's a big number, not because the variation is big, but because I had a lot of data values. I had 107 data values. And so that that affects how big that number is. It doesn't make it big. Now you can have 107 data values and still have a small sum when you do this part of it. But we want to take into account how many data values went into the calculation. And so just like you do for the average, right, for the mean, you add up all the data values, then you divide by how many data values you have. Because just adding them up isn't going to tell you the mean, because it doesn't take into account how many data values are going into that summation. And that's an important part of figuring out where the center is, right? Same thing for variation. It's important for us to know, well, how many data values did we use to get that sum? And so we're going to divide, but it's a little tricky. For a sample, we don't divide by n like you do for the mean. You don't divide by 107 in this case. You're going to divide by 106. And here's where my relatively weak background on, I shouldn't down talk myself. I'm qualified to teach this class, but I don't have a really strong background in statistics. And so I don't know if I can give you an adequate explanation for why we do this. But we are going to divide by n minus 1 instead of just n. And it has to do with this concept called degrees of freedom. And I don't know how much I want to really try to explain it, because it's not really something you need to know. And I don't know how accurately I'm going to explain it. But my understanding of it is the population that we're studying. Now, this is a sample. This is not the population. But the population we're studying has a fixed mean and standard deviation, right? There's some truth out there that and I said standard deviation, and don't worry about that. I haven't defined it yet, so I apologize. That's kind of what we're currently deriving. But there's the result we're trying to get at for the measure of variation for the population is already set. And we're hoping our sample is a good estimate for that population measurement. And given that, I don't know, and it's a sample, so this is where maybe I get a little bit fuzzy on it, but if your value is fixed and you know the answer you're supposed to get, then when you have 107 data values, 106 of them could be any number. Those 106 really don't matter, as long as the 107th one is chosen so that you get the answer you're supposed to get. So 106 of them are free to equal any particular values, but the 107th one really is fixed in order for you to get the answer you're supposed to get. So in this data set, the degree of freedom is 106. And again, if my fear is by recording it and putting it on YouTube, more knowledgeable people than myself might be watching it, and they're going to say, oh, that's completely wrong. And if it is, please leave a comment in the video and make sure to, share your knowledge. Correct me if I'm misstating that. And maybe there's more to it. Maybe there's, a better way of explaining it or more to it than that. But that's kind of my rudimentary understanding of degree of freedom, which has to be taken into account when you're dealing with a sample versus a population. And so we're going to take this number and we're going to divide it by, so let's use that number there, divided by n minus 1, which is 106 in this case, right? N is 107. We're just going to have one less than that. And we get 37.38. Now, and there's more after that, but so this number takes into account, okay, so let's think of all the, issues that it addresses. It avoids zeroing out by squaring each difference so that all the numbers come out positive. And it takes into account the size of the data set by dividing by n minus 1. But we run into another issue. And it was unavoidable, but there is an issue here. So now these are review scores, which really don't have units that we can easily assign to it. But let's imagine for a second that these numbers were in feet, right? So this is 70 feet. This is 90 feet. This is 91 feet. So let's just add a unit to these numbers to see what happens. Now, when we find the mean, we add up all these numbers, 100 feet plus 100 feet plus 100 feet. When you add up a bunch of numbers that are in feet, the sum is still in feet, right? 100 feet plus 100 feet is 200 feet. So adding and subtracting numbers does not change the units of those numbers. They have to be the same to begin with, and they stay the same after you add or subtract them. So we got to be careful about that, right? Because if one number was 100 feet and the other one was 100 inches, you can't add those numbers together. The units are not the same. It wouldn't make sense to add the numbers together. But the units for our data set are all the same. And when we add those numbers together, the result will still be the same units, right? And then when we divide by n, the number of data values, that actually is a unitless number. So there's 107 data values, and it's just a count. And so there's no units, not 107 feet. It's just there's 107 numbers. There's no units on that 107. So we take our sum, which is 9,698 feet. We divide by 107. And so this number, 90.6, would still be in feet. So the point I'm trying to make is when you're finding your mean, the units of your mean match the units of your original data set. If the units of your original data set were in feet, then the mean will also be in feet. All right, so now consider what we've done here. We've taken 100 feet minus the mean, 90.6 feet. Again, the units have to be the same for us to subtract them, for that to make sense. And the units that we get as a result are going to continue to be the same. So 100 feet minus 90.6 feet gives me 9.36 whatever feet, right? So if the units of our data set were in feet, when I subtract that from the mean or vice versa, take the data value minus the mean, the result will also still be in feet. So these are all in feet right here, right? However, when I square these numbers, the units of those numbers also get squared. So the difference is still in the original units of the data set. But then when I square it, now these numbers are, or, maybe this is a better way to say it. This would now be in square feet, right? So when you square the difference, the result you get has units that are also squared over and above what the original units were. Right, so the units here are in feet. When I square that number, the feet get squared also. And so these numbers are actually in square feet all the way through. And so when I add all these numbers up, this result is still in square feet because that's what all these numbers were in. And then I divide by n minus 1. That's a unitless number. And so the answer I'm getting here would be in square feet. This is 37.38 whatever square feet. And the problem with that is that those units do not match the units of my original data set. My data started out in feet, but my measure for variation that I currently have is in square feet. And the reason that's a problem is those numbers cannot interact with each other. I can't take this data value of 90 and add or subtract it to my measure of variation because it doesn't make sense to take 90 feet and add it to 37 square feet. They're not talking about the same thing. You cannot add those numbers together. You can't subtract them. So we get this measure of variation that really is difficult, impossible to interact. I don't know, I'm saying that kind of in a funny way, but this measure of variation cannot interact with our original data set. That's a problem. We need it to be able to interact with it. So how can we fix this? Well, we need to unsquare these units. So if I want to go back to just having feet as my unit for my measure of variation, I need to apply a square root to it. I want to undo the squaring by taking a square root. Again, another concept from college algebra, right? How do you cancel out a square? You apply a square root to it. So if I'm going to do that to the units, I have to do the same thing to the numbers. So I have to take this result and take the square root of that number. So I'm going to take the square root, which I think you can do on here. SQRT is a common abbreviation for square root. I don't know if I have to have it capitalized. So maybe I do. I guess it doesn't seem to care. And then we're going to have it take the square root of that number. Okay. And now we have a number that represents the variation in our data set. It takes into account the deviation of each data value from the mean. And it takes into account the size of the data set, and it's in the units of the original data set. So now it can interact. Now it makes perfect sense to take one of my data values, 90, and subtract this measure for variation, 6.11, because they're both in feet, so they can interact in that way. So that is going to be our gold standard for the measure of variation in a data set. And I wanted to go through that exercise, even though I'm already at 45 minutes. Holy cow. I haven't even really got into I don't know. This is really a large part of what this section's about, but I feel like I have a lot more to talk about. So I apologize for the length of this video as well. But I think it's really important to understand why, because I could have skipped all this. I could have just said, here's how you find the standard deviation, which is what we just found. Here's the formula. Here's the process for doing that. But I want you to understand why it looks the way it does. Why is the formula so complicated? It is a complicated thing. Why did it have to be like that? This is why. We had a lot of issues to address, and in addressing them, things got more and more complicated. But this is the way we measure variation, and this thing is called the standard deviation. So let's get back to that. All right, so is there a better way of measuring variation? Yes, it's a lot more complicated, but this gives us a much better understanding of the variation in our data set, and it's called the standard deviation. So this is a measure of variation of values relative to the mean. It is a type of average deviation from the mean of the data set. And this is the formula. This is what we just did. We just went through this calculation with our big Animal Crossing data set. So think about what all these symbols mean, right? X represents our data values. So X is a data value. It's one of the reviews from our Animal Crossing data set. Minus X bar, remember, that's the mean. That's the sample mean specifically. So we're taking the data value minus the mean, which is what we did just a moment ago. And then we have to square it to get rid of all the negative signs. When we use absolute value, it's hard to work with, so we're squaring it instead. And then we added up all those results, right? That's what this symbol means, right? This is a sum. So we take the sum of the differences squared. We take the difference between the data value and the sample mean squared, and then sum up all those differences squared. The square of those. So I guess if I put it all together, we take the sum of the square of the differences between the data value and the sample mean. It's a really technical way to say that. Then we divide by n minus 1, not just n, but n minus 1 because of that degree of freedom stuff. And then we had to take the square root because the units were off. Right? That's why the formula looks the way it does. Right? And the symbol that we use to represent the standard deviation is S. Excuse me, S. I'm losing my voice already. All right, so it's called standard deviation. Really important concept. It's important in almost any field of research. I would say, I'm saying almost, I feel like I'm understating it. Every field of research relies on standard deviation for affirming results. It's a really important concept. And so this may be your first introduction to it. If you've taken some science classes, especially more rigorous ones, when you do labs, you will consider standard deviation in those labs as well. At least I remember doing that. And I can remember not really understanding what I was doing because I didn't have a statistics class to explain it to me yet. And they're just like, this is just what you do. You find this number and this is what it means. As far as whether your result's good or bad or whatever. But it didn't really make sense to me what it actually was. All right. So that's standard deviation. This is also standard deviation, but for a population. And again, you normally will not use this formula because you normally do not have a population. It's very rare that we actually have data values from an entire population. Most of the time, again, I'm understating it. 99.9% of the time or more, we're working with samples. We just never get to have a population at our disposal. But if you did, and you wanted to calculate the standard deviation for a population, you do not do n minus 1. That's really the only difference here. You just divide by the number of data values in the population. Remember, mu is the symbol for the population mean. But you're going to be doing the same thing. I'm sorry, I'm doing a horrible job of writing. So this is your data values minus the population mean squared. You sum up all those results, divide by n. and that gives you your population standard deviation, which is represented with this kind of funny symbol, which is actually a sigma. So this is a sigma, which stands for sum. That's a capital sigma, capital S in Greek. This is a lowercase sigma, or a lowercase s in Greek, right? And so these are both called sigmas, but that's a lowercase one. So let me go back and modify this. This is the standard deviation that you're going to use because we're always working with samples, but to be more specific, this is a sample standard deviation. All right. Okay. And so we just did this calculation, right? So this was a sample, so we did the n-1, that's what we divided by. And what did we get? We got 6.1. We're going to go one. So again, now that my calculation's over, I go one decimal place, it's 6.1. All right. 6.1. And again, the units of that match the units of my original data set. Maybe I shouldn't have chosen. I thought Animal Crossing, people are going to, especially young people will identify with that because it's a popular game or whatever. But critic review scores, I mean, you can think of that as the unit, right? This is a 100 review score. This is a 95 review score. So this standard deviation is a 6.1 review score. I mean, the units are the same, but it's just not really, it's a really abstract unit. Maybe I should have picked a data set with more concrete units like feet or something like that, or pounds or whatever. Okay, so that's the standard deviation here. There is one other measure of variation that we've already done. So you might say, we got to go through one more exercise like that. No, we don't. Variance is actually part of the calculation for the standard deviation. It's the number that you get before you take the square root. That's all the variance is. It's actually a better measure of variation, but remember the issue was the units were mismatched from the units of the original data set, which makes it difficult to use. But it's actually a better, it's more reliable in estimating the population than the standard deviation is. So the variance is a measure of variation equal to the square of the standard deviation. So if your standard deviation, if that's what you're calculating with your technology, to get back to the variance, you just undo the square root by raising it to the second power, right? So I think, I was going to write it on the screen, but I think I have it right here. So this is the sample variance, right? So again, we have to make a distinction here versus this is the population variance. I just didn't want to type it out in this like funny math font. So sample variance is the sample standard deviation squared. The population variance is the population standard deviation squared. And like I said, the variance, with everything that we're doing with samples, we hope that they are estimating the population version of those numbers. The sample variance is a good estimator for the population variance. The sample standard deviation actually is a little bit off as far as estimating the population standard deviation. But it's still, even though it's a little bit off, it still doesn't do a bad job. And it's so helpful to have it match the units of the original data set that we by far and away use standard deviation over variance in almost everything that we do. Okay, so that's how you find variance. So how do I find the variance for the Animal Crossing review scores? So the variance here is going to be the standard deviation squared, which is going to be 6.1. And again, because I'm doing another calculation, I shouldn't stop at 1. I don't want to use the rounded off version of that number. I should use the precise, the exact standard deviation with all the decimal places to do this further calculation. But I'm not going to have to actually do that calculation because it's on my spreadsheet. It was this number here. So if I take this number and I raise it to the second power, it just takes me back to this number. So it's going to be 37.4 if we go to one decimal place for that. So, but if you don't have, because what you're going to want to end up doing is you don't want to have to calculate this standard deviation by hand. There's technology that will do that for you. In fact, I'm sure this spreadsheet has a square root, not square root, of course it does. I'm sure this spreadsheet has a standard deviation function. So if I do like equal Stan dev is a very common way for that to be abbreviated. No, that didn't work. Stan dev, maybe. There you go. ST for standard, DEV for deviation. And I can just do the same thing I did up here, which is I can give it a list of values, which I think I can do by just cell reference, and it'll do the whole calculation for you. So you don't have to manually subtract, manually square it, manually sum the numbers up. It'll do all of that at once. So let's see if we can get it to work actually. I don't know if this is going to work. What column is this? F2. I don't know. It wants it to be separated by commas. So I don't know if this notation is going to work where it says F2 through whatever. So this may, in fact, not work out very well. Let's see. If I go back up to the top, F2, F3. Yeah, I guess I'm going to have to do comma. Let me see if I just highlight from there. Let's maybe not do that. Let's do it from here. I don't know if it's going to like this or not. Let's just try it. Can't really break it, right? So let's just see. And we'll know if it's right because it should match the answer that we got. Pretty close, anyways. And let me take out that initial. And where am I doing this at here? Okay, see if I can take out that initial F1. Yeah, oh, it worked. Great. So you can see it's a little bit off. No, it's not even a little bit off. I thought maybe because we did. No, we didn't actually, right? We actually went back and put in the 1402. So yeah, it's exactly the same, right? So you see, this is from our manual calculation. This was letting the spreadsheet do the calculation for us. And that's really what you want to do. You might say, well, if that's what I'm going to be doing, why did you spend 30, 40 minutes explaining the calculation? Because I want you to understand what it means. You need to understand the formula. And, when you get this number, if you don't go through this exercise of understanding how that number is arrived at, the number is meaningless to you. I want you to have some understanding of the meaning of this number. So that's why we went through the exercise of step-by-step calculating how to find the standard deviation, so that as you're finding more and more standard deviations in other data sets, you'll have a real sense of what this number means, what it represents, how you arrive at that number, and what it entails. All right. So I'm telling you that I really don't want you to have to manually go through this calculation and using those formulas. I would like you to take this shortcut of just letting the technology do it for you. But I hope that when you do that and you get these results, because you've seen how that number is calculated, you'll have a better sense of it. All right, so that's what you should do. TI-84, same thing. You type your list of data values into that calculator, and there's a standard deviation function on there that will calculate the standard deviation for you. Or it's like 1VAR-STAT. I don't know. I feel like it's been a while since I've done it. I think 1VAR-STATS does it for you. It finds the mean and the standard deviation, finds all the good stuff that you want to know about a data set. So there's various types of technology that will do this calculation for you. And you should take advantage of those types of technology. Okay, so it's 37.4. That's what I wanted to find out. All right, so let's write that down. 37, I'm writing the wrong number. 37.4. But again, this is review scores squared, right? So if we think of the units of these numbers as review score, a 100 review score, a 95 review score, this is 37.4 review score squared. So you cannot take this number and do any adding, subtracting with the original data set. So it's hard to do any further analysis with the variance directly interacting with our original data set. Okay. The round off rule still applies, as I mentioned. For your final results, you want to go one more decimal place than what's present in the original data. But for further calculations, you want to keep all the decimal places. Students run into trouble with that on my stat lab because they're going to be asked for multiple things. And so they'll say, well, when I was asked for the mean, I rounded it to one decimal place. And then I use that number to find my standard deviation. Well, you're not going to get the right standard deviation if you're using a rounded off mean. And so even though for typing it into my stat lab, you want to use the rounded number as your final result for the mean, when you go to do a further calculation involving the mean, do not use the rounded off mean. Use all the decimal places as you do further calculations. All right, so there's one more topic in this section, usual versus unusual values. And I went and looked at the homework, and it doesn't really have a lot of questions about this in the homework for 3.2, but it will in 3.3, I'm pretty sure. And it's a really important concept. So, and I think it gets introduced in the textbook in this section, so I wanted to go ahead and talk about it. And this is also called the range rule of thumb. So a data value is considered unusual if it lies more than 2 standard deviations away from the mean. So we have to kind of have some rule of thumb to use. And this is called the range rule of thumb, right? But some consistent way of knowing when a data value should be considered unusual or not. We don't want to be arbitrary about it or inconsistent where in this case we say yes, in this case. We don't want to just base it off of I'm saying the wrong things. We don't want to base it off of gut instinct. We want to have a rigorous way of making that call. We want to have a consistent way of judging when we should call a value unusual or not. And that's what this range rule of thumb is, if it's more than 2 standard deviations away. And it's kind of connected to this other rule of thumb of if the chance of that data value occurring is less than 5%. So 5% sort of this, I don't want to say arbitrary, but it's kind of where we decide to draw the line between what's considered usual and what's considered unusual. And so 2 standard deviations kind of corresponds to this 5% rule. If it's less than 5% chance of occurring, it's unusual. If it's more than 2 standard deviations away, it has a less than 5% chance of occurring under the assumption of a bell-shaped curve, which I think we're going to kind of assume is the case for a lot of our data values anyways, especially if we're looking at samples. And so there's a connection there, which we'll get more into later. But 2 standard deviations away, it's unusual. All right, and so here is the bell-shaped curve, which, like I said, is a really common distribution for a lot of data sets. And in that case, if you go 2 standard deviations away, so the mean is in the middle of the bell-shaped curve. This is your mean. And if you go 2 standard deviations below or above, you create this range of values here. And if you look at what's the percent of data values to the right or to the left of that particular range, we have 2.5% of data values to the left of that range and 2.5% to the right. It's a little bit less than that, but roughly 2.5% to the left, 2.5% to the right, which together is 5% of your data values. So you have 2.5% that are below that range, 2.5% that are above that range. So 5% of data values are outside of this range that's 2 standard deviations away. And so about 95% of your data values will fall within 2 standard deviations. So again, there's that 5% rule. So these are the values that we consider to be usual or typical that are within 2 standard deviations. But these values we consider to be unusual if they're outside of that range. They're considered to be unusual. Okay, so now that we have a mean and a standard deviation, and it's important to consider the standard deviation in deciding if something's unusual or not. So go back to the beginning of the video, right? Our 2 data sets. 2 would not be unusual in the first data set because of the variation in the data. 2 is a commonly occurring data value, whereas 2 would be unusual in the second data set because it was always equal to 3. So there was no variation in that data set, so we wouldn't expect there to be variation if we were to collect further data. So 2 would be unusual in that second data set. The important thing to realize there is that the variation in the data really determines what should be considered usual or unusual. And this is how it shows up in our rule of thumb. So if we look at our Animal Crossing data, the mean was 90.6 approximately, and the standard deviation was 6.1. And so now we have a way of calculating what review scores we should consider to be usual or unusual. And so I think back to that review score of 70 that just keeps sticking out every time we look at that data set, right? Because it's so far away from the rest of them. Would we consider 70 to be an unusual review score for that data set? We can find out now. Now that we have a measure of center, 90.6, and a measure of variation, 6.1, the standard deviation, we can make an assessment on whether we think 70 is unusual or not. Is the data spread out enough? Is it varied enough that 70 seems to be common? Or is it more compact around a certain number of data values where 70 kind of is outside of where we would expect the data values to show up? Right. And so let's do this calculation real quick to find the minimum usual data value. Now, you gotta be careful here because students will get this confused with minimum value. So the minimum value in our data set is 70, but that's not the minimum usual data value. So what's the lowest data value that I would consider to be usual or normal or typical in this data set? That's what we're about to calculate. All right, so let's undo those stray marks there. So multiplying this by 2, again, I'm trying to avoid having to grab a calculator. We get 90.6 minus, this will be 12.2, right? 2 times 6 is 12, and then 2 times 0.1 would just be 0.2. So let's subtract those two. We would get 80, it's going to be 78.8 if I'm not no, 77.8 I think would be correct. All right, so 77, right? Because 90 minus 12 will get us to 78. Or maybe it should still, okay, I'm thinking 90 instead of 90.6. It's going to be 78 is correct, 0.4 I think is what we would get there. So this would be the lowest number that I would consider to be usual for a review score of Animal Crossing. Anything below that would be considered unusual. All right, so if we think about that range, I like to put this on a real number line. So the mean here is at 90.6. I'm going to go 2 standard deviations to the left, and that gives me 78.4. Let's try that 8 again. 78.4. If I go 2 standard deviations to the right, what do I get? And this one you might kind of balk at because it's going to go outside of the possible range of values. But 2 times 6.1, and we're going to add that to 90.6. So we're going to get 90.6 plus 12.2, which is going to give me over 100. It's going to be 102.8, right? And that would be the maximum value that I would consider to be usual in this data set given the variation in the data. 78.4 is the minimum value that I would consider to be usual given the variation in the data. So this is going to be 102.8. So, which makes sense because given the data set that we looked at, is 100 an unusual data value? No, it occurs a bunch of times. So I wouldn't consider 100 to be unusual. So you really can't max out. You can't have an unusually high review score for Animal Crossing because the highest review score you can get is 100, it appears, and that's not going to be unusual. But you can bottom out, right? There is a lowest value that we consider to be usual, and you can get review scores that are below that. And so this range is what I would consider to be my usual review scores for Animal Crossing. Anything outside of it, not that it can happen, but anything above 100 point, sorry, I'm saying the wrong number again. Anything above 101.2 would be considered unusual, which can't happen. So you can't have an unusually high review score. But anything below 70 point, sorry, I'm saying the wrong numbers. I guess, again, as these videos get near over an hour, I start to my mind starts to fall apart. Any numbers, any review scores below 78.4 would be considered unusual. And those kind of review scores can happen. And in fact, we had one in our data set, right? So 70 is unusually low as a review score for Animal Crossing. Right? 80 is not, right? Is 80 unusually low? Well, if you look, again, if you try to use your gut instinct on it, and you look at the, what am I doing? Okay, go back a page or two. You look at this data set and you say, there's so many hundreds, there's so many 90s. So maybe your gut instinct might tell you 80 looks a little bit on the low end. Maybe that's unusually low. But when we look at the numbers, When we look at the mean, we look at the standard deviation, it tells us how varied this data is. 80 is not unusually low. That is a common review score for this game. All right, so let's go back to this. Right. So is 80 unusual? No, because 80 is in this usual range. The minimum that we would consider to be usual is 78.4. So 80 is within the usual range. So that's how you would interpret that. All right, so that's minimum and maximum usual values, not to be confused with minimum and maximum values, right? The usual, and that's why I have it bold and underlined. That extra word makes a big difference in how you interpret what we're actually looking at here. 78.4 is not the minimum value in our data set. The data values can go lower than that. That's just the minimum that I would consider to be usual or typical or common. Anything below that can happen, but it would be considered unusual or atypical or uncommon, right? Okay. So we just did that. What are the minimum and maximum usual values for Animal Crossing? Is a review score of 100 unusual? No. Right? It's within our usual range. I didn't mark that one, but it's, our range is from 78.4 to 102.8 that we consider to be usual. 100 is within that range, so 100 would be considered normal, typical, usual. 100 is not unusual, right? So is a review score of 100 unusual? No, it's not. Is a review score of 70 unusual? Yes. Now, I asked these questions before actually knowing the answer. I wasn't 100% sure where 70 might fall within the usual values, but it is unusual. It's below the minimum usual value. Okay. Estimating standard deviation using this range rule of thumb. I already spent so much time giving you this background on standard deviation. So when they say range rule of thumb, they're talking about both of these concepts. So these two formulas are part of the range rule of thumb. And this formula we're about to look at is also part of the range rule of thumb. So don't be confused by that description. If they ask for minimum or maximum usual values using the range rule of thumb, you should use these formulas. If they ask you to estimate the standard deviation using the range rule of thumb, you should use this formula. So an estimate for the standard deviation is to take the range divided by 4. It's a very simple calculation, and it's merely an estimate to give you a ballpark figure of what the standard deviation might be without having to go through the very complex, complicated, rigorous calculation that we did earlier. Now with technology, it's a little bit silly to want to estimate. I don't know, maybe not. I mean, there still could be situations where it's like, I don't want to actually collect data and plug it into a calculator to get an actual standard deviation. I just want to have a sense of what the standard deviation might be, off the top of my head. And that's what this formula is for. Now remember, the range is the maximum value minus the minimum value in your data set. So you can get an estimate for a standard deviation without actually even collecting a sample, if you have an idea of what a maximum value might be and what a minimum value might be for that particular data set. So you kind of estimate what's a maximum, what's a minimum in this case, and then from that you can do a back of the envelope calculation of what's the standard deviation for that what's the standard deviation for that sample likely to be, given what you know about the data values for that particular kind of data. So for example, if I wanted to know the standard deviation of ages of professors on campus, this has been a problem I've seen in the textbook. It doesn't translate well to my stat lab, so you don't normally see it on there because everybody will come up with a slightly different answer. And, my stat lab needs the answer to be more concrete. It can't be variable like that. But if I wanted to have an idea of the standard deviation of the ages of or let's just not even do professors. What's the standard deviation of, let's do professors. What's the standard deviation of ages of professors at a university? I don't want to collect a sample of ages of professors at universities. That would take some effort. That would take a lot of work. And then even after I got a sample of 30, 40, 50 ages, I'd have to go through that really tedious calculation to get the standard deviation. Or even if I wasn't going to do it by hand, I'd have to plug it into a spreadsheet and then let the spreadsheet do it. But still, there's a lot of work involved there. It's not that important to me to want to do that much work to find that information. So I could just do this range rule of thumb calculation. What's the oldest professor that you can think of? What's an age? What's the oldest that a professor might be at a university? Now, you can have professors that even after they retire, they stick around and still teach a few classes. So maybe 80. I think at Dodge City Community College, we had a professor. He wasn't full-time, but I want to say he was probably pushing 90 and teaching a pathophysiology class. And so let's say 90. Maybe we could have a professor that's as old as 90 as a maximum age. What's a minimum age for a professor? Well, I'll tell you personally, I started teaching at the age of 25, which is about as low as you can go, right? You need, especially at a university, you need at least a master's degree. So if you do everything right on time, 4 years of bachelor's degree work, you're done at 20, graduate high school at 18, get your bachelor's degree at 22, and then 2 more years to get your master's degree. 24 is about as young as you can be to be a professor at a college. So let's say 24. I was 25, but let's go with 24. And so that's a pretty good estimate for what a range might be for a sample of ages of professors at a university, right? They could be as old as 90, as young as 24. You wouldn't really expect the ages to go much higher than that or much lower than that. And so this is a good estimate for the range. So to get an estimate for the standard deviation, we will take 90 minus 24 and divide that by 4. And so let's see, can I do this? I feel like my brain's really turning to mush now. It's getting close to dinner time. I'm hungry. So let's see if I can do this calculation without a calculator. So 90 minus 20 would be 70. Go 4 below that, we get 66. 4 goes into 66. And again, I shouldn't use equals. This is just an estimate here. 4 goes into 6 one time, carry the 2. 4 goes into 26 6 times, carry the 2. And then we have a remainder of 2 divided by 4, which will be half, right? So we get about 16.5. So that gives me an estimate for what the standard deviation might be given a sample of ages of professors at a university. It'd be around 16.5 is what you would expect. But again, it's not a perfect calculation. It's going to be in that neighborhood. It could be lower, could be more like, I would expect it probably to be lower because that's this estimate indicates, but it's just an estimate. Okay, so that's what we're saying here. The standard deviation for a data set can be estimated as the range of the data set divided by 4. I skipped past that screen kind of quickly, but this is the formulation of those words, and then we just did an example using that. Okay, this video is getting really lengthy. I think I might need to take a break in my recording, maybe even do a separate video. I don't want my video to be like 2 hours long, but there's one more topic I forgot about, which is the standard deviation of a frequency distribution. So I think I'm going to go ahead and pause for a moment, and then I'll resume. I might need to just go ahead and eat something. I covered all the material for this section so that based on what we covered in the video, you should be able to do the homework problems. They're kind of repetitive relative to what we've already talked about. So for the standard deviation of just a data set, there actually is an alternate method for calculating it. So if you take the formula that we developed previously, you can actually mathematically rearrange things, and you get this version of the formula. So I'm referring back to this one here. See if I can find it. All right, so this one here. So if you take this formula, you can actually rearrange it and make it look like this. And in some ways, this is an easier calculation, especially if you're not using technology. So what this tells us to do, it looks more complicated, but it would be easier, is to take all of your data values squared and then sum those results up. So you square all your data values, and add them all up, and that would give you that sum. You would also just sum up your data values without squaring them first. So you'd sum up all your data values, get that result, then square that. And that would give you this part here. Here you'd multiply that sum by n. And this means you don't have to take each data value minus the mean and add and square all of those and add all of those up. All you have to do is add up your data values and the square of your data values. And then you could use those numbers plugged into this formula to get the standard deviation. I don't use this formula myself. I don't really like to use it as far as introducing the concept because it kind of masks what the standard deviation actually is doing. So it's not incorrect, but it doesn't really quite address, what the standard deviation is, I feel like, as adequately. The reason I even bring it up is because just to make you aware of it, for one thing. So this is another way you could calculate the standard deviation if you wanted to, but also to explain why this formula looks the way it does. So one problem you will have on your homework, and I don't think I would put this on an exam. It's a really tough calculation to do, which you won't be able to use technology to do for you. You have to do this kind of by hand. But you will be asked to find the standard deviation of a frequency distribution. So like I said, it'll be on the homework, but I don't think it would be on the test. But, let's wait until you see what the practice test looks like for my class anyways. And if it's on the practice test, then yeah, you better get ready for it. But I usually don't put this kind of problem on the test. Mean of a frequency distribution, yes. That's one I expect you to be able to do, but standard deviation is a little bit more complicated. So this is the formula for the standard deviation for a frequency distribution, and you can see why it looks different than what we saw earlier, because this actually is more in line with the alternate formula for the standard deviation. And so we have x squared times the frequency, and what that is, x is the class midpoint, squared times the frequency for that class, and then we add all those up, and that gives us this term here, which we would then multiply by n, which is the number of data values in the data set, minus the standard deviation of the frequencies times the class midpoints, this is an exercise that should be familiar because that's how we had to find the mean. So you take the frequency for each class times its midpoint, add all those up, and then square that result. And then you divide by n times n minus 1, take the square root, and that will give you an estimate for the standard deviation when you're working with a frequency distribution. So let's see if we can go ahead and do this calculation real quick together on the frequency distribution for the Animal Crossing and see if it gets us close to the actual standard deviation. All right, so remember the class midpoint here is 65.5. Okay, sorry, not happy with that 5. And this is 75.5, midpoint, 85.5, and 95.5. And so here's how you would want to approach this. And this is kind of an old method that people would use before there was technology for calculating standard deviation and other things like that, is you would just take a table of your data values and then just extend it by adding more columns each time you had to do a different calculation with all the data values in your set. So what we want to do here, there's a couple different calculations. I'm just going to add a new column right here, even though it kind of cuts into the title. For this column, what we want to do, let's do this one first. We want to take, for every class, we want to take the frequency, oops, I hit the wrong button, take the frequency times the class midpoint. All right, so we're going to do this one first. So here I'm going to take the frequency times the class midpoint for each class. And so, sorry, I'm just really unhappy with the way I'm writing for some reason. Okay, and we'll write the result here. So we're going to take, and I didn't really do it this way in the previous video, but this would be a really good way to handle finding the mean of a frequency distribution. We're going to multiply these together. So we're going to get 65.5 times 1, which is 65.5. I guess I will have to use a calculator now because these numbers are going to get a little bit out of control. 75.5 times 11. So it's going to give me 830.5. We'll have 85.5 times 59, which would be 5,044.5. And then we'll have 95.5 times 36, which is going to be 3,438. All right, so that's taking f times x. All right, this is x right here. This is f right here for each row. Then we want to sum that up. We want to add up that entire column, all of those calculations. So we're going to add all these up, and this is going to give us the sum of x times x. All right, so we have 3438 plus 5044.5 plus 830.5 plus 65.5. And that's going to give me 9,378.5. Right, just like we got before. I feel like this 5 is bothering me now too. All right, then what do we want to do with that? And it's going to make the number really, really big, but we want to square that. Right, so we want to take that sum and then raise the sum to the second power. So not the individual numbers, but once we have the sum, raise that to the second power. So I think I'll save that for a moment. So let's go ahead and just copy this down. This number is 9,378.5, and we will want to square that. N is 107, right? So we can go ahead and plug that in. All right, so that's N. Next, I need to find this sum, which means I need to take my class midpoints and square them first, then multiply by the frequency for each class, then add up all those results. So we'll extend the table. Maybe I'll go ahead and do this here. I will square each midpoint and put it in this column. Right, so we have 65.5 times 65.5. Oh, maybe I should have picked a different data set with nicer numbers. 4290.25. Don't round it off. You need to keep all those decimal places. 75.5 times 75.5. That's squaring 75.5. And we get 5,700.25. 85.5 squared. Oh, I messed up. 85.5 times 85.5 be 7,310.25. And then 95 squared. 95.5 squared, which will be 9,120.25. So that's squaring all of our x's. And then what I want to do is take the frequency times those x squareds. And that's what I'm going to put over here in this last column. So I'm taking the frequency times the x squared. So these two, not this one, but these two right here. So this number times 1 is just going to stay that number, 4290.25. Then we're going to have 5,700.25 times 11. All right, so let's go ahead and do that. 5,700.25 times 11, which is going to give me a huge number, 62,702.75. We're going to have 7,310.25 times 59, which is going to be 431,304.75. And then we're going to have 91, how do I want to say this? 9,120.25 times 36. Which is going to give me 328,329. All right. Then I want to add that column up. So I will add, let's use a different color here. I'm going to add this column up. So I'll have that last number. I'll just add to that. 431,304.75. Plus 62,702.75 plus 4290.5. Sorry, 0.25. See if I can fix that. 4290.25. And I end up with 826,626.75. All right. And so that is, this number here is the sum of the frequencies times the x squareds. So now I can plug that into my formula here. And so it's going to be this huge number, which I don't know if I'll have room for. 826, it's not even going to write it for me. 826, 626.75. Sorry, I'm writing it really small, but I want to make sure it fits. All of that's going to be divided by n, which is 107, times n minus 1, which will be 107 minus 1, which is 106. So the hardest part about it is just getting these sums. And then once you have those sums, you can kind of think of this like a formula where you just plug the numbers in. Replace the summations with what they actually total out to. Replace the n's with 107. And you get this formula here, which you can then calculate. And so we're going to have that big old number that we just, which is still in my calculator. So I'm going to take advantage of that. Multiply that by 107. Which makes it even bigger, minus, and I don't know how this calculator is going to handle it, so I better write that number down. It's a really big number. It's 88,449,062.2. Right. I just don't know if it's going to work. Minus 9378.5. Let me see if I can square that here. Squared. Enter. Okay. Yeah, I think it worked. Okay. So I'm going to skip this now. I apologize. Things are getting kind of hard to follow, I'm afraid. But so what I did, because I'm using my iPhone, I don't usually use this calculator. I wasn't sure if I could square it and subtract it at the same time, but I think it worked. And so I just, instead of typing this number again separately, I just multiplied these two together, and then in my calculator did minus this number squared, and just had my calculator kind of manage all those numbers for me all at once. And what I ended up with after I subtracted is 492,800. All right. Over, let's clear that out. We're going to have 107 times 106. Which is 11,342. And so we're going to take that 492,800 divided by 11,342, and we get 43.449, and it goes on beyond that. 1, 2, ... And sometimes if you're not careful, students will say, there's my answer. That's my standard deviation, even when it's not a frequency distribution, but when it's the other, like when you're finding a regular standard deviation for a regular data set. I can remember I've had a couple students where they just always forgot this last step, which is the square root. Do not forget the square root, right? I haven't taken the square root of that number yet. So really that's the variance that I have. The standard deviation is going to be the square root of that. And so let me take the square root of that number, which is right here. And I get 6.6 when I round it to one decimal place, which is really not bad considering that the actual value is 6.1, right? So when we did the standard deviation with the actual original data set, we found the standard deviation to be 6.1. Estimating it from the frequency distribution, which isn't the original data set, it is an estimate, but we still got 6.6, which gets us pretty close to that. So that's how you find the standard deviation from a frequency distribution. And that's why I'm hesitant to put it on the exam. It's a very long set of calculations. There's a lot of room for error, which makes it hard to grade as well. But it's just a lengthy problem. And it's something that it's not something that we're going to need later in the course. Now, if this was something that was going to be relevant to a later topic, then yes, I would probably put it on the test and give you a few of these on the homework, but you've been exposed to it. You'll have to do it once on the homework. You've seen it in this video, so we've talked about it, but I don't think it's something that we need to have on the homework, especially if it's not, I don't think it's something that we need to have on the test, especially if it's not something that we're going to need to use later in the course. All right, so skipping this homework problem, skipping this homework problem. These are things we've talked about already. And maybe I'll talk about this one as well. But so this one I want to talk about because I didn't actually include it in my lecture in the earlier slides like I should have. It's something I forget. And I was kind of going off of my colleague's notes, and she didn't have it in there either. So it's something that obviously gets overlooked pretty easily. But it's an interesting thing to consider. So we have these two different data sets. And let's say we want to compare the two data sets, and we ask ourselves the question, which data set has more variation to it? The systolic numbers or the diastolic numbers? Which one's more variable? Which one has a bigger spread of values? Now you might say, well, that's easy. Calculate the measure of variation for each data set and compare the results. Unfortunately, you can't really compare those results. So the measure of variation is the standard deviation. The problem with comparing the standard deviation of one data set with the standard deviation of another data set is that that number only gives you an idea of the variation within that particular data set. It's only informative within that realm. And if you try to take the standard deviation from one data set and compare it to another data set that exists in a different realm with a different set of numbers, it's not really comparable. It doesn't really translate. So case in point, the standard deviation, let's see, I'm trying to think, what was the standard deviation here? I can't remember what it was. I calculated it already. I guess it is kind of big. The point I want to make, well, I guess it doesn't really work because these numbers are kind of in the same range, 80 to 100. The numbers that you get for the standard deviation aren't just affected by the variation in the data, but the size of the numbers themselves. And so I don't have a good example to compare this to, but just imagine if we had these numbers, which are around between 80 and 150, somewhere in that range, and a data set where the numbers were in the millions. Well, because that data set has numbers in the millions, the standard deviation is going to be affected by the size of those numbers. And so the standard deviation might be a fairly large number, like 10,000 or something, which sounds like a big number, but it's not that big relative to millions, right? And so whereas 10,000 with this data set would really be impossible, but right, that'd be a really large number for variation if we're working with numbers this small. Whereas if we're working with numbers in the millions, 10,000 isn't really that much variation with such large numbers. And so, so if you have a data set where you're in the 100,000s versus the billions, for example, that makes a difference, whatever the standard deviation is. How do I want to say that? So that even if both sets had the same standard deviation, so if we had one set where we're in the 100,000s and one where we're in the billions, let's say the standard deviation is like 50,000. Well, for the 100,000 numbers, that's a pretty big variation. That relative to the size of those numbers are all over the place. If the variation's 50,000, if the standard deviation is 50,000, whereas if we have numbers in the billions and the standard deviation is only 50,000, that's not very much variation at all. Those numbers are really closely clustered together in that range, in the billions range. So they might be like all around 1 billion, 1 billion, 100 million or something like that, somewhere really close together, relatively speaking. So the point I'm trying to make is standard deviation is relative to the data set that it comes from. I probably just belabored the point a little bit too much. So if I want to make that comparison, if I want to look at two different sets of data where the magnitude of the data is a little bit different, like here, systolic numbers are bigger than diastolic numbers. So there are two different data sets on two different levels of magnitude. If I want to compare them and try to determine which of these sets seems to have the greatest variation, I have to take into account the size of the numbers in each set when I make that comparison. So what we use for that is something called the coefficient of variation, which is what you see here. The coefficient of variation, which is abbreviated CV. And it's a simple formula. which I'm having to look on my paper because, like I said, I don't always cover this like I should in class, even though I think it's a really important thing to talk about. It's just the standard deviation of that data set divided by the mean of that data set, and then times 100 to make it a percent. You're converting it to a percent. And so if you want to compare the variation of two different data sets, then you find the coefficient of variation for each and you compare the coefficient. Don't compare the standard deviations, compare the coefficient of variations from each data set to get an idea of which data set seems to exhibit the most variation. All right, so let's go ahead and do that calculation here for this set. Actually, I'm not going to do it on the screen here. So as you saw on my spreadsheet, I went ahead and typed out the data. These are the systolic numbers, these are the diastolic numbers, and then I found the mean and the standard deviation ahead of time. So the mean for systolic was 127.2, the standard deviation was 18.2. The diastolic mean was 73.3, standard deviation of 13. Now, even though 13 is smaller than 18, that doesn't mean it had less variation in the data, because these numbers were just smaller to begin with. And so relatively speaking, 13 may actually be quite a large variation here and make that data set have actually more variation amongst its values than the systolic numbers, even though the standard deviation is a slightly bigger number. To know for sure where we have the greatest amount of variation, we look at the CV, we look at the coefficient of variation. And so we'll find that by taking the standard deviation, so this number here, divided by the mean. And then, I think I can do this, times 100 to make it a percent. So we get 14.3% for the systolic coefficient of variation. Let's do the same thing here. We'll just copy and paste, right? It should adjust it. And we get 17.8% for the diastolic. So actually, even though the standard deviation is smaller as a number, as a percent of the data set itself, as a percent of the mean, which, again, compares it back to the size of the numbers in the data set, the diastolic numbers exhibit more variation. Right, so that's how coefficient of variation works. I wanted to make sure to address that because there is one homework problem, I think, at least one, on actually, in fact, this was it, right? This was a homework problem. So you'll have at least one homework problem on that topic. So I wanted to make sure you were prepared for it. All right. The other thing that you might see on here is a problem like this, which says using the empirical rule. I didn't refer to it that way, but it's talking about this chart here. So you might want to, copy down the details of this chart on your notes when you go to answer that question. So when it talks about, well, how many data values would you expect to be between two standard deviations? You should say 95% of the data values. If they ask you what percent of data values do you expect to be within three standard deviations, you would put 99.7%. That's how many would be within three standard deviations of the mean. If it's just one standard deviation away, 68% of the data values are within one standard deviation of the mean. And so that's what the empirical rule is talking about. So these are the numbers you'd want to use, depending on, how many standard deviations they're referring to. I'm really sorry about how long this video is, and I'm trying to end it, but I just want to make sure I've addressed everything. So what approximate percent of healthy adults with body temperatures are within three standard deviations? It'd be the 99.7%. Right, that's what you'd put for A. What is the approximate percentage of healthy adults with body temperatures between 97.34 and 99.42? Well, to figure that out, you have to figure out, well, how many standard deviations away are these numbers from the mean? The mean is 98.38. The standard deviation is 0.52. If we go one standard deviation away, I don't know, would that be one standard deviation away? That'd be 0.8. No. So one standard deviation. So, what's one standard deviation away? We have 98.38. That's the mean. How far is one standard deviation away from that? Well, if I add the standard deviation, which is 0.52, I will get 0 here. I'll get 9. I get 98.90. So that's not one standard deviation. Sorry, I didn't mean to cross it out. This is not one standard deviation away. Let's add another standard deviation, another 0.52. So whatever the standard deviation is, add it to the mean successively until you match the number that's given in part B. And that tells you how many standard deviations away you're considering. And from that, you can figure out what the percent is, right? So if I add another 0.52, I'll get 99.42. That's exactly what this number is. So this is 2 standard deviations, which means 95% of the data value should be between those two numbers. Because however far away this one is, this one should be the same distance below the mean. Because I don't think they're going to mismatch it on you, because we're not there yet. So, okay. So that concludes finally the video on section 3.2. I'm sorry for all the meandering at different parts of the video. I will see you in the next video for section 3.3.